Okay, thank you very much. Okay, I will first start with the guiding documents. Today, my skill workshop, which I will be doing, is based on Introduction to Energy and Climate Modeling. And I have two simple examples. In the first example, I will show you the theory behind the linear programming and the duality theory, and how linear programming is used to solve the optimization of the systems. It doesn't have to be only the energy system. It can be transport system or a production system. The theory behind optimization is similar. And in the second example, I will show you a simple baseline energy system where there are two generators of electricity, one coal and the other wind power plants, and the one polluting and the other non-polluting technologies, and how these energy sources are used again to optimize the baseline energy system. And in the guide, I included instructions for installing GAMS. GAMS is a solver which is required to do the optimization solving. There are also other optimization softwares, but the one I will be showing, the MessageIX and the other simple example, will be using the GAMS simplex solver. And I don't know if you have installed it. If you click on the guide, you can see the steps for MessageIX installation. MessageIX, as you may well know, it is distributed, is developed as an open source software and distributed by EASA. Before that, there was Message5 software, again developed by EASA, but distributed by the International Atomic Energy Agency. It is a packaged software, can be distributed to countries as a non-profit research software application. But today, as we are in an international environment, I will be providing the examples using MessageIX. So the first step is the GAMS installation. Where you can install the latest distribution of GAMS from this link, which I can write also in the chat. And from here, depending on your operating system, you can install GAMS. I don't know if you have installed at the moment GAMS. Or do you want me to wait for you to install GAMS to your computer? You can also try out running the sample files afterwards. I have included them to my repository, where you can access again from the instruction sheet, the link, the second link. If you click on that link. You can download the presentation, my presentation file, and the sample files, which I will be describing during my presentation. Okay. So what the model is, the model is an abbreviation, message is an abbreviation for Model for Energy Supply System Alternatives and their general environmental impacts. It's actually, it has quite a lot of history. It was developed during the 1960s, 70s by EASA, and it pretty much coincides with the oil crisis which the world faced at that moment. So if you find an opportunity to look at the first case studies, first energy modeling exercises, you can see that there are very different technologies used in the energy mix. You can see oil, you can see coal, you can see gas, which is not natural gas, but which is gas extracted from processing coal. You can see a lot of nuclear power in the modeling exercises, which was done at those times. But with the transition of the energy systems, with the mainly the market liberalization and the disintegration of the production chains from supply to transmission to distribution, the energy system has changed quite impressively, actually. And now we can see more the renewable energy sources, technologies, and we can practice smart transmission and distribution energy systems. And we can also practice together with that district systems and also energy storage systems, which have developed quite impressively in the recent years. The model takes as an input the baseline energy structure, whether you're running it globally, regionally, nationally, or subnationally in a district in one of your countries. You first have to define the baseline energy system structure, from resources to primary energy sources, which are extracted from the nature, the secondary energy resources, which are the conversion of the primary energy resources like electricity or the fuel, the oil products, and after that, final energy, and eventually the useful energy, where we use in our daily lives, in production, in industry. And we have to define the flows and the prices for the base year energy system structure. And secondly, okay, yes, I have a comment in the chat. And we have energy demand projections. These energy demand projections I will simply show in my second example. We can generate using the socioeconomic projections like GDP growth, like population growth, like land use, or food requirements, land requirements, and so on. We can use these together with scenarios to generate energy demand projections. And these are used as an input, exogenous input in the message model. And we have technology and resource options. The technology options, we can include both the existing technologies and the future technologies, which we can expect that will penetrate globally, regionally, or nationally to energy systems. And we have technical and policy constraints. The technical constraints are mainly due to the operation and maintenance of the power plants. It can be thermal power plants, or it can be renewable power plants, and the policy constraints. Of course, there has to be policy constraints in the energy system, because when we think about the energy transition, this transition will be from one point to another. If you can look at the history, there has been transitions in the past, like in the 19th century from steam engine to coal combustion, and in the beginning of the 20th century, in the transport system from horse carriages to motorized vehicles, there has been both slow and sudden transitions, but these transitions affect the society, the economy, and the world in general. So we have to moderate these transitions through policy constraints. And defining these as an input, the model looking into the time horizon, whether you use it for short term, like 2030 or 2035, medium term until 2050, for example, or long term together with climate models until the end of this century, you do an optimization, you run the optimization solver so that you calculate the development of the energy system in an optimized way so that this energy system can meet the energy demand projections and can satisfy the technology, resource options, and the technical and policy constraints. So we have as the output of the model the primary and final energy mixes, the emissions. These can be environmental or thermal emissions and waste streams, the environmental impacts, the resource use, the land use required for extracting the energy resources, including the biomass, the import dependence, how nations, whether there will be the energy system will contribute to energy security of regions or countries, and the investment requirements which are required for the development of the energy system. And some mathematics in the simple form. What we have is an objective function where this is the sum of the costs related to the activities of technologies in the energy system, from resource extraction to primary energy consumption to transmission of the secondary energy sources and until the final and useful energies. Our objective is to minimize this total energy system costs. As a time horizon can be medium or long, the discount rate affects our objective function greatly. Discount rate, this is, in a simple term, the depreciation of the time value of money. What we spend now is not the same as what we will spend 20 years or 50 years after. So we have to take this into account, but this discount rate affects the timing and the content of our investments greatly. And we solve this objective function, we minimize this function under a constraint where the main constraint is our demand function. Our energy system, our activities have to supply this demand, which we defined exogenously in the model. To define the energy demand, we rely on socioeconomic variables. We have energy and climate policies which have an impact on production. And this impact, at least on the short scale, has to be mitigated. In the past, during the Kyoto Protocol period, this was much of an issue that the policies for energy and climate, for transition and mitigation and adaptation to climate change, these have a negative impact on the GDP, which had to be mitigated. But recently, we talk more about the benefits of energy and climate policies in the medium to long term, because we have also the innovation, the digitalization, and we have more production options where we can compensate the initial loss which we can face by implementing the energy and climate policies. In general, we use energy models iteratively with economic models because we define the final energy demand or the useful energy demand exogenously based on our current price assumptions. But the model, as investments are made, as the energy system structure changes, the prices also change. So we have to take this changes in the prices into account for reassessing our energy demand projections. So in general, energy models are used iteratively with macroeconomic models where we have a production function and we have the prices and we have the substitution effects where we can solve this problem iteratively until we have convergence of the quantities of energy demand and the prices. However, we again have constraints here. Our energy model is constrained by the availability of capital, both monetary and non-monetary capital, and the environmental impacts, where our energy infrastructure, our energy system has to be resilient to environmental impacts. And the economic model is constrained by the availability of capital with prices and the availability of labor, which is calculated with labor wages. And again, the energy models, they mostly foresee a major transition in the energy system, considering the energy and climate policies, usually a reduction of fossil energy sources like coal and oil. But these transitions also have a big impact on the production and the economy. So these have to be taken into account with the evaluation of prices and wages. When we think of global modeling, historically, countries had been aggregated based on their similar socioeconomic characteristics, like the North American countries, South America, Sub-Saharan Africa, the OECD countries, the former Soviet Union countries. In global models, usually these countries are aggregated together. There are also some special separate countries which are evaluated, which could have a high carbon intensity in production or high population growth. And these countries could also be included separately in the models. And plus, we define a global trade region for market clearing of global energy markets. And there are energy sources which cannot be easily classified into national boundaries, like international aviation and shipping, bunker fuel demand, which are, again, high carbon intensity fuel sources. We have in the nuclear power cycle the uranium resource extraction, which is interestingly, the resource extraction of nuclear fuel is mainly done in countries which do not generate nuclear power. And the nuclear fuel cycle, which is again an energy intensive sector. But the energy system is more dynamic. It is difficult to treat it only with yearly or 5-yearly periods. It depends on seasonal, daily, and hourly human activities. And in the energy markets, with the market regulator and the system regulator, there are always load taking and load shedding at system marginal price, which has to be considered again. There can be constraints coming from the physical energy transmission system. Some countries can have interconnection links with other countries, which can make them more resilient to outages, but some countries can operate with low transconnections or in an island state, like Turkey or South Korea, which can be affected more from these energy market activities. And there are trade-offs between economic growth and climate policies, which has to be considered in energy modeling. Now, this is the first example which I will show you, which you can also download from my repository with the link in the guidance sheet, the transport.gms. This is actually a simplified version of the GANT 6 example in the GAMS model library. The simplification is to do a graphical solution so that the theory of linear programming and the duality theory can be visualized. And here in this, first of all, before moving to the simple transport model, do you have any questions up to now? Okay, if not, I will ask you a simple question after presenting this slide. Here we have two supplier cities, one from Seattle and the other from San Diego. And this supplies the transport canisters. Seattle can supply maximum 300 canisters. San Diego can supply maximum 400 canisters. And for these canisters, there is a demand from New York with 600 canisters. This is a single year optimization, so there is no discount rate here. We solve only for current year. And this cost of transporting canisters is based on the distances between the supply cities and the demand cities. From Seattle to New York, it is 2,500 miles, and from San Diego to New York, the distance is 3,000 miles. And we have a transport cost of $90 per 1,000 miles. So our objective is to satisfy the demand in the New York market from supply capacity in Seattle and San Diego. And we need to minimize the total cost. The solution is actually trivial, as the model will prefer transport from the shorter distance from Seattle first. So the model will first consume the 300 canisters from Seattle because the cost is lower. And after that, to satisfy the total demand, the transport cost, the remaining amount is supplied from San Diego. Now we can simply solve this problem from our mind, but I will show you how we can solve it using linear programming and duality theory. And if you have GAMS installed, you can open the file transport.gms, where the supply and demand markets are predefined. The parameters for capacity of supply plants, demand of the market, New York market. The variables where X is the shipment quantities and Z is our total transportation cost, which we want to minimize. And these are the equations. Now, our mathematical solution, we have actually two solutions. The first one is the primary solution, where our objective is to minimize the total system cost, which is Z. C is the transport cost and X the activity of transport from supply markets to demand markets. And this is subject to our constraint, where our constraint is to satisfy the demand, our main constraint. And of course, our activities have to be greater than 0. Our secondary solution is to maximize our welfare from this supply and demand balance. As we have demand from the New York market, this demand is initiated with a price. So with the price and the demanded quantity transported from supply markets, we have a benefit from supplying these canisters. And in total, together with the prices of this utility, we have a welfare. And this welfare is subject to the costs related to our activities, which can both take our utility positive or negative values. And these are our equations, which we will solve graphically. Our objective function, Z, is the cost of transport from Seattle to New York, which is $225, times the activity, plus the cost of transport from San Diego to New York, which is $270, times the activity of transport from San Diego to New York. Sorry. Our constraints are, our main constraint is to supply the demand. We have to supply the demand from the New York market, from our transportation from Seattle and San Diego markets. Whereas we have the constraints for production. From Seattle, we have a constraint of maximum 300 canister production. And from San Diego, we have a constraint of maximum 400 canister production. And finally, our transport activities have to take values greater or equal to 0. And from each equation, we have a utility. We have a utility from supplying to demand. We have utilities from supplying from Seattle and San Diego capacities. And we also have utility from our activities, transport activities from Seattle and San Diego. So from linear programming, we can generate our secondary solution as the maximization function of welfare, denoted by W. And we have positive utility, positive welfare from our demand, satisfying our demand. But we are constrained from our capacity of production from Seattle and San Diego. So if we reach this constraint of production, we could have a negative welfare depending on our utility. And the second equation, this welfare equation, is subject to the cost of transport from Seattle, which is U1 minus U2 plus U4, which is less or equal to 225. And the cost of transport from San Diego, which is U1 minus U2 plus U5 less or equal to 270. Now, when we put our primary solution equations to a two-dimensional graph, we have the black line, the demand line, where we can satisfy the demand from a mix of transport from Seattle and San Diego. And we have a constraint for production from Seattle and San Diego. From Seattle, we have a constraint of 300 canisters maximum. And from San Diego, we have a constraint of 400 canisters maximum. And when we also apply the greater than and less than signs, we have an area where we can find our solution space. But our optimal solution has to be the minimum cost of this transportation. So looking at the Z and giving values to Z at this point where production capacity of San Diego and Seattle interact, or at the corner solutions, we can see that the minimum cost of Z equals $148,500 US. We can see that this is on the point where the transport amount from Seattle is 300 canisters, and the transport amount from San Diego is also 300 canisters. This is actually the first solution which we obtained. This is a trivial solution because this solution provides the minimum cost for this transaction. But when we look at the secondary solution, we will again the same solution. The U3, U4, and U5, these I set to 0. The main reason comes from economics, the economic theory, microeconomics. In the solution, we are not constrained actually by the 400 canister maximum amount from San Diego. So the utility of increasing this 400 with an additional amount is actually 0. This does not affect our solution. And also we are not constrained by U4 and U5. Increasing these amounts by 1 again does not affect our solution. So I can say that U3, U4, and U5, our utility from these equations are 0. And by that, we can also solve the secondary solution in a two-dimensional graph, where giving the same cost values to the welfare, we can see that our utility, our welfare is maximized when U1 is 270, meaning that if we increase our demand with an additional unit from 600 to 601, we can benefit from additional production from San Diego with a value of $270, which is our U1 value. And our U2 value is actually the difference between the value from transport to San Diego, $270, and transport from Seattle, the value, which is $225. And we can check this by increasing the U2 constraint from 300 to 301 This means that we can produce one more unit, one more transport canister from Seattle. But to increase this production by one more unit, as our demand is again 600, we have to reduce our production from San Diego. So our additional utility is the difference between 270 and 225, which is $45. And here I want to ask a question. As you can see, the total cost Z is equal to the total welfare W. Can you say why they are equal? Is this a coincidence? At least, what do you think about this? Just a guess, maybe. You can also write in the chat. Okay, I will give you 2 minutes so that you can think. Just I want from you your idea why they are equal, why Z and W are equal. Is this a coincidence or can there be a meaning? By the way, in the guidance sheet, I also have a form which I hope you can fill so that I can know you more, at what profile you are attending. I suppose currently I only have one answer. Yes, I have only one answer. If you can fill out my form, I would be very happy. Okay. Well, they are equal because we have some major assumptions in this model. For example, assume that you will go to a market to buy bread, and the bread in the market costs 2 euros. But the market which you go has increased its price to 3 euros. So what you will do if there are no costs for you for changing the market, if you can easily go to another market, then you will not buy this bread for 3 euros and you will buy the bread again for 2 euros. Then this market, which is selling the bread for 3 euros, will not be able to sell, and he or she will be out of the market. So at the end, with our general assumption that you can reach a supplier without any costs for transaction, the prices, the values of the transport from supply to demand equals to the marginal costs of transporting from supply to demand. And as our activity is the same in the prime solution and the secondary solution, And as our price equals to the marginal cost, economically, we can say that our total welfare equals to our total cost. Otherwise, when we want to minimize the total cost, if we accidentally have some activities which can reduce our costs, which can affect our demand, then naturally we would have the minimum cost, which is zero, when we have no activity. But having no activity, we would have no welfare. We would have no activity and no welfare. So naturally, when the minimized costs and the maximized welfare converges, which is for linear programs, this will be mostly a corner solution, then we can say that we have the optimum solution. Coming to energy system modeling, of course, the energy system modeling, we have more challenges comparing to a supply of some goods from supply market to demand markets. We have multiple policy objectives which have both synergies and trade-offs between each other. And historically, we can define this as an energy trilemma, where we cannot maximize the security of supply, the energy security. We cannot minimize the carbon emissions, and we cannot minimize the total costs. At the same time, we have to implement policies so that we can have innovation, we can have better behavior, consumer behavior, that we can achieve this dynamically in the medium to long term. We have a great ambition where actually still our emissions are increasing. I'm very curious at what point we will have a peak emissions. Because as far as I know, up to now, we do not have a peak emissions, and we will have another COP conference by November. And I just wonder when we will expect to see peak emissions. But we have a great ambition that we will have a peak in a close time. And after that, we will have a rapid reduction of carbon emissions, possibly with or without negative emission technologies, depending on both their maturity and the social evaluation of these technologies. And this climate target, is based on multiple factors: the greater freedom of consumers, producers, and prosumers, which are rapidly expanding both in European Union countries and in also other countries, which will affect the prices, hopefully lower the prices, help small businesses with expanding business activities, not only with climate policies, but also innovation and digitalization policies. These also promote small businesses and prices, lowering of prices. We would have increasing competition and choice, and eventually we would have increasing economic growth. But we have multiple stakeholders in this issue. Just looking at an investment of a new power plant, there are many stakeholders which both share the benefits, but also hold the risk from this financing investments. And of course, the climate policies, these have to be global. We all otherwise just implementing net zero in one region, whether that region is a highly polluting country or region, this will not solve our climate change problem. It has to be implemented globally, and it has to be implemented timely. But we have to take into account also the local impacts of climate change in our policies. Distant problems can make us lazy to act, but when we face the threat very close, in a very close proximity to ourselves, this can support policymaking, regional policymaking, and local policymaking a lot. My second example is by using message IX, and in the installation sheet, actually the exact installation document you can reach from the EASA website, which I also included the link. But this is a sheet which I use with my students, which is much more simplified and which helps previously to solve the installation problems which I had faced in my classroom lectures. In either case, you can try both. You can also try from this guidance sheet, or you can also use the EASA installation website, which I also provide here in this link. And there are also installation movies in the YouTube, the recordings from previous workshops, which you can also consult for installing Message IX. And here I will show you the baseline scenario, which includes the coal power plant and the wind power plant to satisfy the electricity demand of Westeros, which is from the Games of Thrones. I'll just open the tutorial file. Okay, you have some of you filled my poll. Just I will check your poll responses at the end of the workshop. Yeah, I'm sorry. I opened the wrong file. Sorry, I'll change. The solver in MessageIX is again GAMS, but the interface is from Jupyter Notebook using Python code and connecting with the MessageIX server, which is named IXMP. This is an abbreviation, IXMP. I is for integrated, X for cross-cutting, MP is the modeling platform. And if you have used Jupyter Notebook before, or if you haven't, it's quite easy actually. You have cells which you run one by one, consequentially. And these cells are either codes, Python codes, or Markdown, which is texts. You can also run the texts. This MessageIX is open source software, and it has inline documentation. First, we have to import the libraries. Pandas is for visualization. IXMP is for connecting with the database. And MessageIX is for converting the Python code to GAMS input for solving the optimization problem. It takes some time in my computer. Okay. When the star is gone and when we have a number, it means that it's completed, the cell running. And we continue one by one. We create an instance of the IXMP platform as MP in our computer. And now we will populate this instance with the baseline scenario for Westeros. Here, where we have coal power plant and wind power plant technologies, which are generating electricity and with transmission from the grid, from secondary to final energy. And we eventually have the useful energy demand as light, and together with the technology for light bulb. And the model horizon spans 3 decades from 690 to 720. This is if you have watched the series. This is far in the future after the events of A Song of Ice and Fire. And we, of course, have a discount rate of 5% as we have a modeling horizon. Our solution will also be affected by our discount ratio. And this is a simple representation of the model. One interface which we are connecting to the model from Jupyter Notebook with Python code. And we have connected with the IXMP database, and we have created an instance in our computer. And using Python code, we will and MessageIX, we will generate JDX input files, which will be used by GUMS for optimizing the energy system. We have demand for electricity, which is correlated with production. We have a GDP profile, which is similar to the beginning of the 20th century world historical profiles as an increase. And the model assumptions for defining the useful energy demand. There are 40 million people in 300 AC, and we will calculate 300 years after, assuming a similar population growth to Earth in the same time frame, and a per capita demand for electricity of 1,000 kilowatt hours. I can continue from sample file. Now we populate our model. Where we define our country, we have defined our time horizon, and we set our levels of energy, the commodity, electricity and light. Our levels are secondary, final, and useful energy. We have 4 technologies: the coal power plant, the wind power plant, the transmission grid, and the light bulb. And our operation mode is standard. We first have to generate the energy, calculate the light demand, and we do that based on GDP, population, and our assumptions for growth. And we populate by adding the parameters, our grid parameters for power plant technologies, our constraints, where we have our coal power plant is available during the time horizon, whereas here we define simply our wind power plant, which is available 36% of the time. And we have the light bulb, which is again available on demand. We have the lifetimes of the technologies. We have to calibrate for the base year. As the model, the optimization solver tries to optimize starting from the first year. Sometimes there can be major transitions in the first modeling year because naturally our existing energy system, which we use as a baseline, as a base year, is not optimal because there are many social or economic constraints which we have to consider besides only the costs of the energy system. So to avoid this major transition in the base year, in the first year of the model, we have to apply soft constraints so that we can calibrate for the first modeling year. And our objective function is again the minimization of the total discounted energy system cost. We have the investment costs where coal is cheaper and wind power plant is more expensive. This was the case actually in the recent past for solar power plant. Before the rapid cost reduction in the solar PV panels, usually the models applied high costs for solar PV, but with the rapid reduction of the solar PV technologies, currently model users apply much lower costs compared to what they applied like 5 or 10 years ago. We have fixed costs, which are valid both if we operate or we don't operate these technologies. We have variable costs, which can be dependent on fuel or maintenance. And eventually we convert these inputs for solving with GAMS and running GAMS from Jupyter Notebook interface. We can see that we have found the objective function, the total discounted energy system cost, which satisfies the light demand for the time horizon in Westeros. Now, looking at the results, you can look at the results both from GAMS, because there's a GDX file in GAMS, but the simple way is to use the reporter, which is a accompanying package together with MessageIX. First, we have to import the reporter package. Again, it takes some time. Okay, it took a bit more than I expected. So I have already generated the plots. When we look at the activity, we had calibrated the first model year. So we have both coal power plant and wind power plant based on the shares ratios which we defined in the calibration. But after that, as the cost of coal power plant and is lower than wind power plant, and the availability of coal power plants to generate on time compared to wind power plant, we can see that there's a substitution from wind power plant capacity to coal power plant capacity for the baseline model results without any energy policy or climate policy constraints. And we can also see that the capacity of coal power plant increases for the substitution from wind power plant in the baseline scenario. We have some additional capacity of wind power plant in the first model year, but this is as a result of our soft constraint to have a share of electricity generated from wind power plant in the base year. And when we look at the prices, actually applying the soft constraint in the base year, we increase the energy system prices in the first model year. This is quite unreasonable, actually. This kind of price difference would not be accepted by a policymaker. This is actually what the society has to forego for achieving the baseline energy mix, which we defined as soft limits in the model. This application, this defining of the coal power plant and the wind power plant as two similar technologies actually is a source of modeling bias, because when we define them, we define as coal power plants superior and the wind power plant inferior technologies based on the costs and their availabilities to generate electricity on demand. Actually, renewable energy is characteristically different than baseload generation. We have an unlimited input of energy in renewable energy sources of wind and solar power. And when we define them as two similar technologies, we, in energy models and energy and climate model, we have to define them as separate characteristics, where if we define them as similar, we would have a modeling bias, which we have to try to mitigate by applying energy and climate policy constraints. But scientific advancements helps us a lot to solve this issue. We can use more the prediction of energy resources, renewable energy resources, where we can predict based on the climate and hydrometeorological data, we can predict the availability of solar power, wind power, hydropower with higher efficiency. So instead of defining a capacity factor, if we define these renewable energy technologies with time series on when we expect them to be available, we can satisfy our supply and demand more effectively, and this would remove the problem of defining renewable energy technologies as inferior to fossil or nuclear power plant technologies. And the curtailment requirements, where there is increasing share of renewable power in many countries, and based on the fluctuating demand, which is fluctuating based on demand and price and our habits of living, the curtailment requirements might favor renewable energy expansion together with innovative technologies such as in the energy storage technologies, or more innovative technologies such as electricity to fuel or electricity to power technologies. And these will favor renewable energy technologies more, which should be represented more in energy and climate models. We also have a time horizon difference in the models, where our net zero targets are mainly for 2050, which is not very quite long, which we can define as medium term. But our climate targets are for the end of this century. Our temperature increase targets of hopefully 1.5 degrees Celsius is by the end of this century. So we have to consider how the model considers this time horizon. The message model, in general, implements a perfect foresight approach. However, there are also applications with limited foresight approach. But in general, the message optimization software assumes that there is a central planner of the energy system, which decides on the evolution of this energy system based on the constraints for achieving the energy demand and also satisfying the energy and climate policies. However, our decisions are quite short-sighted. This is actually what we see in the COP meetings, where in mostly every COP meeting, we are always behind of the target, where there is always requirement for higher ambition. And this is mainly because of short-sighted policymaking, which also affects the energy and climate policymaking in countries and regions. Now, finally, coming to the discount rate. As I mentioned, our model results are very much affected by the discount rate. The baseline scenario for Westeros used 5% discount rate, which is reasonable, actually, which is a reasonable discount rate so that investments do not have to be delayed and large investments could be done without having a high cost. But if you consider this discount rate, there are also ethical questions. The first one is looking at the time horizon 2050, 2100, there will be future generations which will be affected by our activities, but they will have no effect on our decisions currently. So the first question I would ask is, why should I take the burden of spending today when we are not having expectedly high productivity like the future? We don't have future technologies. So our productivity is lower compared to the future if we have the development rate continuing and the costs are high currently. This is based on the idea that the future generations would be better off than our generation because they will have the products, the fruits of innovation, technology, and they could better solve these problems with much lower costs. But the second question is, why should the future generations take the burden of our decisions, our costs, when they can be much better off without them? Our emissions, our pollutions, our way of living, they will affect the future generations, which don't exist at the moment. And this raises an ethical question which has to be solved globally. And this is a very challenging issue considering the short-sighted of the energy and climate policymakers. But there has been solutions for similar problems in the past, and this gives us hope. The main example is actually the Montreal Protocol to limit the fluorine gases emissions, which affected and still affects the ozone hole in the stratosphere. But there are also other global problems like biodiversity loss, and there are a lot of international agreements for this. But there is also a problem of nuclear waste disposal, which is waiting again for us by the end of this century. And thank you very much for listening to me. I hope this was a beneficial introduction to energy modeling for you. It is sometimes difficult to make distance workshops. If you can answer my poll, I would be very happy. I would know this would be good for me to also evaluate myself. And you can also reach me by email in case you are curious about anything or want to ask a question or want help for your activity.